Good morning, everyone. Welcome to Quantum Mechanics 1. I'm Joseph. I'm from Mexico. אני מדבר קצת עברית. אם אתה רוצה לשאול משהו בעברית זה בסדר. But in general the course will be taught in English. Okay, so first let's start by telling me your names.
Nitai.
Tai? Itai?
Nitai.
Nitai. And you? What about you?
English name Joseph.
Joseph?
Yeah.
Also?
Same for you.
Great.
Chinese name Qingquan Sun.
How?
Qingquan Sun. Chinese name.
Ah, okay. It's very hard for me to pronounce. Tin, Swan,
Sun.
Swan?
Yeah.
Okay. Great. Okay, first of all, I wanted to discuss some details of the course. As you can see, there's not a lot of people here. I spoke with Richard, which is a lecturer of the course, the professor. He told me that assistance it's mandatory. Okay, anyone who doesn't come to more than 30% of the classes will not have right to succeed the course, to pass the course. So assistance is mandatory. And the percentages will be, I think, I don't remember, so you have to ask Richard about it, but it's 70% exam and 30% homework. Okay, this is Quantum Mechanics 1. I will be located in room 213 in the second floor of this building. Anything you ever need, please don't hesitate to ask me. You can go there, you can send me an email. I usually am working there. If you want to be sure that I'm there, please send me an email and I will try to respond as soon as possible. My mail, I will put all this information also in the Moodle, in the web page of the course. And my mail is Joseph. This is my mail. Yeah. All the lectures will be here, also the exercises. And do you have any question about the course? No? Okay. So let's start. And okay. Do you know how quantum mechanics, why is there such a thing as like quantum mechanics?
I know it began when we quantized photons and also the Niels Bohr description of the atom, right?
Right. Great. Okay. The first at the end of the 19th century, there was a crisis in physics. Like, people said that since we understand Newton and everything we can see with our eyes was Newtonian, everything was right. But there were some things that were like the skeletons in the closet, you know, that people said, okay, that is because we haven't studied the problem good enough, but we will get the answer sooner than later. And the thing is that actually they couldn't be more wrong. Actually, the Newtonian mechanics fail to describe nature at a certain point of energy. Okay? In general, in physics, we have different types of regimes, of energy regimes. Like, we have the big things and fast things. My spelling is not very good, so if you don't understand anything, please let me know. Which are described by relativity. Okay. There are the normal things, let's say. Which are described by Newton mechanics. Or classical mechanics, whatever you want to call it. And there are the small things, which are described by quantum mechanics. The goal of this class, of course, is to focus in this. And just for you to know, this relativity also can be paired with quantum mechanics, the special relativity. There are two types of relativity: general relativity, special relativity. Special relativity can bring together with quantum mechanics in what we know is quantum field theory. Okay, but we will not touch. That's the last thing you will hear in this course about it. Okay. The idea is that one of the things that was happening at the beginning of the last century was that people discovered that there are such things as atoms, and there were plenty of models. I'm sure you learned them in high school, and probably you have heard them in chemistry courses. I don't know if you have taken some of them.
Modern physics.
Okay. Yeah, right. In modern physics, you talk about a lot of these things, and this is just a reminder. This, like this class, is only a reminder of things you are supposed to know before entering the course. Okay. If you don't know anything, please ask me questions. Okay. So the idea is that we have electromagnetism, that was at the end of the last century, was the greatest theory. Everyone was obsessed with electromagnetism. Even Lorentz thought that everything in the world could be explained in terms of electromagnetism. He even wrote a theory where he derived that the mass of the objects can be explained by the electromagnetic interactions. The thing is that nature is not that way. It was a great theory. You can have great ideas that doesn't resemble the nature, the physical nature of our universe. He even wrote how to derive everything. Unfortunately, nature is not like that. So it's a theory that went to the garbage. Okay, so one of the things people noticed, it was that if you have a piece of metal, right, and you throw to it light, like electromagnetic waves. Of course, electromagnetic waves don't look like this because they are transversal waves. Okay, there are electrons here that pop out of the material, right? And we saw that, but this is not consistent with the, people were thinking that light was a wave, right? We saw that in Young experiment. It was proven. Maxwell equations even go you can derive the wave equations of the light from Maxwell's equations. The thing is that if you have something and you hit it with another thing, like if you have a particle, small ball, and you hit it with another thing and this goes out, this must not be a wave. We don't see this type of phenomena occurring in nature. This should be something like a particle. Okay, so Einstein was the first one to think, like, to propose a model, and he thought about the photon. Do you know what the photon is? Well,
Light particle.
okay, exactly. So the idea was that these waves are composed by little particles, which are called photons. And when a photon hits an electron, it can moves, like, take it from the material and to free it. Okay. So how can we express this? The model of the Einstein model was very simple. Do you know the photoelectric effect? This everything that I just said is called the photoelectric effect. Can you help me write the
I
equation?
don't remember the exact equation, but maybe it's H ni equals H ni.
Right. Like, we have the energy of the photon, which
Minus the field.
minus this is the work function.
Yeah.
Okay.
Yeah.
I'm going to explain each term of this. Okay. So this is the energy of the photon, which while solving another problem, which is called the ultraviolet catastrophe, Max Planck derived that the energy for a light particle should be h nu, right?
Yeah.
Where this is a constant,
And ni is the frequency.
which will be your best friend in this course, and this is the frequency. So this is the energy of the photon, right? And this is, and V is what we call work function. Okay, the idea is, what is the work function? Do you know?
Do you want to see?
Don't worry, like, it's okay. You're not supposed to know. Like,
Can I
it's
say
sure.
the work function is, I think, the function that sticks the electrons inside the window, and it's the minimal work we need to do with the energy of the photons to excite electrons outside of the window. Right?
Exactly. Okay. It's in other words, it's the function that the material has to grab the photon. It's the power of the material to grab the photon, right? The electrons.
Yeah, electron.
So it's how hard the material is pulling the electron. So if you have this process where you have this electron here and you hit it with a photon, you need at least to free the electron, you need at least energy enough, like, to be more than what the material is pulling the photon, the electron, sorry, and the rest of the energy, it will be the, like, if you have more than that energy, this is the energy of the electron. If the photon carries more energy than the work function, the resultant energy will be the electron's energy, right? By conservation.
Yeah.
Do you understand why? Am I being clear?
What do you mean?
Okay, so this is the energy of the photon, right? I'm going to put it like this. Okay, so you hit an electron with this energy, right? Which is the energy of the photon. The electron then takes the heat, and the process is described by a conservation of energy. So the total energy of the electron should be the energy that was wasted in pulling out the electron, plus the exceeding energy.
Yeah.
that the photon had.
So the photon is absorbed by the electron.
Exactly.
Oh,
Exactly. It's a complete inelastic collision.
yeah.
Okay?
So the energy of the electron would be just a kinetic energy?
Right. At the end, we say that the electron is free since it's not in the material anymore.
So we just move.
Yeah.
Okay.
It's free. Okay?
Like the photon gets it out of the potential wave or something like that? Potential well or something?
Okay. Like this is something that we will address later in the course.
Okay.
But yeah, you have like the electron is trapped here, just to answer your question. And let's say that this is the last energy level of the material. If you pop out, if you hit this with a photon, this electron will go out from this potential well that is defined here.
Okay.
Okay? It's just schematic. We will address this later in the course.
Okay.
I don't want to go around it very much. Okay, so this took me a while. So, okay, so the idea is that we know that there are, like, light is a small piece of something, right? Do you know what quantization means?
Yes.
It can't be continuous.
Sorry?
Not continuous.
Right, exactly.
It's discrete.
Exactly. You're breaking the continuum limit and you're entering to something discrete. Instead of having a line like this, you have things like that. This is continuum and this is discrete. Okay? So another failure of electromagnetism was the atom. Like at the beginning of the last century, Rutherford realized that there should be a positive nuclei in the center, which is here, right? This is a model that is not okay. And there were electrons surrounding this nuclei, right? Which are negative. Okay?
This is the Rutherford model?
This is the Rutherford model.
Okay.
Okay? In general, like, I don't want to go into the details, but can anyone guess what is the problem with this model?
It will lose energy.
How would you lose energy?
And the electron wave, it will continue to
So
shoot the wave.
Right. Exactly. Okay, so the problem with this, you can say like, okay, this is positive, this is negative, those things attract, but I'd address you and tell you, okay, how about the Earth and the Sun? The Sun is attracting the Earth, but there is conservation of angular momentum, so the Earth doesn't fall into the Sun, right? You would tell me, okay, and I will tell you there's some sort of equilibrium here working such like that. What is the problem with that argument?
yes.
Sure.
This is an electric particle, and when accelerated, he emits light, an electromagnetic wave, and then he loses energy because the wave is energy, and so we will lose energy, and then it will collapse into the nuclei.
Exactly. Just like that. So we have this electron that it's surrounding the nuclei and it's losing energy because the velocity vector, it's changing, so it's a particle accelerating and therefore it is emitting radiation. So it's losing energy. Turns out that they made the calculations for how fast this model will collapse, like how fast the electron will collide with the proton, which is here. This is the hydrogen atom, which is the simplest. And it turns out that it's a fraction of a second. So we couldn't live in a reality where atoms will collapse in a fraction of a second. Like, think about it. All the matter that you're seeing couldn't be held like for more than 0.001 second. So the classical theory failed catastrophically. Okay, so we need something else. The first one to address this problem, like to have a model, was Niels Bohr, which Nitan already said, with the Bohr atom. The H continues to move here. Okay. His main idea was, do you know the formula for angular momentum? It's this. Right? So his idea was that electrons must be fixed at a certain have a certain energy, and they must be fixed there. Like they are not moving towards the nucleus. Okay, so he just said this must be equal to some number times the angular momentum constant. Like this is a number which is dimensionless. Every time you see a model, you have to ask about the dimensions, right? You're like this as physicists, this will help you every time. Okay, so this has units of angular momentum. Do you know the units of angular momentum?
Because it would be, I mean, according to this definition, that would be meters squared over a second.
Right. I'm missing. Wait, see, you don't tell the mass here.
Oh yeah. Okay. So kilogram meters squared over a second.
Right. Another way to say this is joules times second. Okay?
Yeah.
Okay, so an h bar is a pretty small number, which is so this is the order of the system. Like you can see that it's pretty small things that we are studying here. Okay, next, do you know? Okay, so now the acceleration for an electron is described by Newton's law. Like we want to do a classical model, right? We're trying to derive a classical model with this condition, which is Bohr's quantization. Okay, so we start by saying that the centripetal acceleration is a. Do you remember this formula from mechanics? Yeah?
Yeah.
Okay. So, do you recall what is the formula for the electric force?
EQ
Square.
Yeah. Okay. And then.
Yeah.
Oh, because it's the same charge.
So you have the exactly.
Okay. And K, maybe the Coulomb constant.
Okay, we are going to use 4 pi epsilon 0, right?
Okay, and then over R.
Over r squared.
Right.
Or r, what is over r?
The energy, right?
The potential, right?
Yeah.
But the potential is without the square.
Yeah.
Okay. Okay, so we have that L square must be. Of course, if you are taking the, like, we are saying that these are orthogonals, right? Because it's orbiting here, right?
Yeah.
So we can write that L, let me put it here, L must be air M air B, right?
Yeah.
Okay, so you know the cross product is, okay, so I will derive everything. So L will be M times air B sin theta, right?
Yeah, I can do the right hand, do R and then B, and then the cross product would be upwards.
Exactly.
Okay.
And since they are orthogonal, the theta angle is 90 degrees. So
the sine is 1.
this is exactly. So we can say that this holds, right? For our model. Okay. So let's keep here. And let's apply Newton's law for these equations, right? How do we do that? It's pretty easy. We have E squared times 4 pi epsilon 0, 1 over r squared. And it's equal to m b squared over r, right?
Yeah.
Do you follow? Everything
Yeah.
okay? So this will cancel out with this, and we put the m here, multiplying the r. Do you agree? Okay. So we have now a relation to the velocity, which is this. Okay, m squared r squared, and now we just substitute this here, which is 4 pi epsilon 0 m r. The one m cancel with this m, and we have this equation for the angular momentum squared, right? Let me see. We can cancel this r with the r up there.
Right.
Okay, if I'm doing some trick that you're not understanding, please let me know. You can ask anything. And if I'm being a bit messy as well.
Oh, can I just take a photo of this? 'Cause
Sure,
I want
sure.
to copy it.
Sure, there's also a recording that we will upload, but of course.
Okay, thanks.
Sure. Okay. Okay, the next thing is that we have this the Bohr condition. Let me change the color. Remark that. This is our condition, right? So this must be equal to n squared.
H bar.
Right. And now from here, we want to see how far the electron is from the nuclei, right?
So find the radius.
Exactly. So we want r. Okay. Just we want to know the size of the atoms in general. Okay. Sounds like a very interesting thing to know, but I don't know if for everyone in the world would be useful. For us physicists, it would be. Okay, so sorry. This will be n squared h bar squared times 4 pi epsilon 0 over and E squared. Do you agree?
Yeah. Wait, you forgot the M, the mass.
I forgot the M, right. You are completely right. So this is M here.
Yeah.
Right? Let me just see that this is okay. Okay, so this is our model. This is the size of the atom. Do you notice anything strange here?
It's discrete, like you have,
Why is it discrete?
because it depends on the N bar.
Right. I forgot to write here, but n depends. It's a positive natural number. Integer, sorry. Positive integer. Or a natural.
Yeah.
I'm not mathematician. Okay. So yeah. Let's define this new quantity, right? As the Bohr radius, okay? Let the Bohr radius be, this is notation, be h bar 4 pi epsilon over m e squared. Okay? This is the Bohr radius, and you can see that we have a better formula for our radius, which is r equals n squared times AB. Right? So as you can see, since h bar, imagine the size of this thing. If h bar is squared, okay? Everything, like, I'm going to give you the number. I don't have it here. Well, you can check in home that this is a very, very small thing. Well, compared to our universe. And you can see that it depends on this number. So it's not that the hydrogen atom is fixed, is of a fixed size. It can be, you have the nuclei, and it has a lot of possibilities here. Okay? And this is, let's say, this is n equal 1, n equal to 2, n equal 3, and so on. And you can see that it is a quadratic formula. If we plot, you see all the board, right? If we plot here, it's just the positive axis, right? And on the radio, it will be something like this, right? Like some parabola. In my imagination, this is a parabola, but it's discrete, so it only takes integer values. Okay. And now we want to find the energy of the electron. Okay. To do that, okay, I will use this part. Of hydrogen atom. Okay? So the idea is that we know that the energy is the kinetical energy times the potential energy, right? And this will be something like this. So we can use the formula we have here. Where do we have?
We have
Here.
squared equals, yeah.
So we know that this is 1/2 e squared over 4 pi epsilon over 1 over radius. This is just a bit of algebra. Which is just you see it's the same term. This is just half of it. So we have minus half, like, well, I'm going to put it like this, e squared over 4 pi epsilon 0.
You do 8 pi.
Hmm?
Instead of half of that, you could just do 8 pi.
Right, but I want to leave the 4
Oh.
pi here.
Oh,
Okay?
so 1 over 2.
This is 1 over 2r. Exactly. So now we want to put everything in terms of Born's radius. Okay. So this would be this is okay. Bohr, and this is the 0, right? Because this is when n it's 1. So it's the starting point. So this will be the energy of the hydrogen atom is minus e squared over 4 pi epsilon 0 over 2, and this is the radius, okay? So we have a formula for the radius here, right? So this is a naught, and this is n squared. So this is the formula for the hydrogen atom in Bohr's model. Okay? The goal to this course is to learn a bunch of things that will tell you that this is a good approximation, but we can do better. Like, at the end of this course, we will see the hydrogen atom in the quantum mechanical version, which is the best approximation in the classical limit. When I mean classical limit, I mean slow, like moving at slow velocity. Okay? I read once a book that said that all of modern physics is dedicated to understanding better the hydrogen atom. Okay? You will see that when you see perturbation theory next course in quantum mechanics 2, you will see that you can add a lot of small details into the quantum mechanical model of the hydrogen atom. Like what happens if, you know, there is a, if you put a small electric field, what happens with the hydrogen atom, what happens if you put a magnetic field, everything of that type of things is what we learn in quantum mechanics. But the greatest thing of this is that we have a model that, think about this just for a second, like this is the order of magnitude of where quantum mechanics is happening, right? And we can describe it, and we have good experimental results that are like we did a bunch of math that explain perfectly most of the experimental results in quantum, like for this system. And surprisingly, it's very different from what we see in the world. Like when you see something, you know that it's there, right? And you can move this marker. You can move it continuously, right? But if you try to do that with an electron, it will be like it jumps from here to here suddenly. Like it can only jump like from some step. It cannot go continuously moving from one point to another. It's mind blowing.
So it just disappears and then reappears?
It's not that disappear. Well, you can think about it like that. It's like the only movement it is allowed to do it's by jumping, like destroying it in one point and reappearing in this other point. This is,
I mean,
sure.
in the very second or in the very instant when the electron is disappearing and then reappearing, wouldn't the atom collapse?
No, the thing. Okay, so the thing is that we are going to see this, but it's not actually disappearing. Like it is, it can have like the electron is at one point, like at one energy level, and then when you start putting energy in it, suddenly the electron it can be in what we call a superposition of states, which this course is to learn what that word means. Like superposition, it's very magical and mystical thing. Don't worry, we will see that and we will address that at the time. But the thing is that okay, in quantum mechanics, everything, the information of the particle is contained in what we call the wave function, which it will be presented to you in the lecture with Richard. And what happens is that the wave function, instead of being at exact point of the energy, you like if you put, you need to put exactly this energy, right? If you put less than this energy, the jump cannot be made, right? This is what we saw in the photoelectric effect 20 minutes ago, right? Okay, so I'm not going to spend much more time in this, but the idea is that if you put just enough energy, so the atom can, the electron will expand its wave function over space, and it will appear here. And if you make a measurement, it has a probability to appear here. Okay?
It has a probability to stay there too?
It depends on how much energy. Okay. We will address that question. Take this question, and in 3 weeks we will answer.
Okay, just for the calculation here.
Sure.
You said that the potential here is the electric potential, right?
Right.
So why is it E squared instead beforehand?
I said...
Because before you said that, I don't remember quite well the...
Sure. Let me... No, okay. So, right. I was talking about the electric field.
Oh, okay.
I messed up.
No, it's okay.
It's E squared.
Yeah.
You know, you have the... Since the force is... I'm going to show you. You know this formula, right?
Yeah.
This is the force, this is the electric field, and this is the charge, right? Joseph, also agree? Okay, so the idea is that if you have the electric field, is only with one E, which will be the source of the field. Okay, and if you put okay, so the energy, you know that the work is the integral of the force times this, right?
Yeah, so it would be with D squared.
Yeah.
Yeah. Thanks.
Sure. Sorry, and correct me if I do anything like that. Please let me know. Okay, so this is like the reason I am telling you this is because the address of this course is to derive the best model we have to explain how matter is formed and how it is brought together and the best thing in the world is that such a different type of world in the microscopic view will lead us to have this stable and nice world where everything moves continuous. This is mind-blowing, at least for me. Okay, so now we finish with the physical part of the lecture, and we are going to pass to the mathematical tools that we will need to this course. Okay? Do you know what time is it? Can you tell me? Okay. Did you saw Fourier series? Are you familiar with that?
Yes. What was it?
Yeah. Fourier series?
For the I know.
Yeah?
Yeah.
Okay. I don't know French pronunciation, so I call it Fourier. I think it's Fourier or something like that. Okay, so what time is it? Okay, so I have a bit of time. Okay, do you remember what is what orthogonality means? Orthogonality. It's a big word, a big fancy word for mathematics.
What, the two vectors are?
What happens to this if these two vectors are orthogonal?
It equals to 0.
Right. Orthogonal is perpendicular. Okay?
Yeah.
It's a generalization. We know perpendicular for vectors. Now, do you know if these vectors are with complex numbers? Do you know how we write this? Okay, I'm going to teach you. So, the vector that is in the left, you do you know that A1, it will be something like this, right? Right?
Yeah.
B as well. So the idea is that the vector in the left, you are going to put it in a row vector. You are going to do transpose and complex conjugation of each element. What do I mean by that? It's just A1 star. I'm going to quit this and put an asterisk.
Wait, each entry is complex?
Yeah.
Okay.
Like everything, like these vectors, I don't want to mess up, but I don't know if you know this notation. A, B are in the complex, This means,
okay.
the only thing that this means is that these are three-dimensional vectors, with each vector, each component is complex. Okay? It's just fancy notation. If you don't like it, I can erase it from the board. And the way we do the vector product is like this. Right?
Yeah.
We can think these are just matrices. Can you help me? Telling me how this matrix multiplication looks like?
So it is A1 star B1 plus A2 star B2
Right?
plus
And B2.
A3 star B3.
Right. Okay, so in order for this to be orthogonal, this must be 0, right?
Yeah.
If this is 0, then these vectors are orthogonal, right? Okay. So let's do one. Okay, so now, do you know that?
Oh,
Sure.
because I haven't seen it before. Okay.
Okay, do you know we can generalize this dot product to functions? Did you know that? You didn't saw that in linear algebra? Like, okay, so this is called dot product for vectors,
Right.
and there is a generalization which is called inner product, right?
Oh, I didn't study linear algebra 2. I think I studied in linear algebra 2.
Okay, yeah, sure.
You mean change a1 equal a3 to a vector and plot the many functions and get the slope in Z?
Again? So,
I do you mean that you change a1 equal a3 to vectors and you get the answer, you get a series of functions and get answers? You mean that?
no, it's
No.
a bit different.
Okay.
Okay, these in principle, these are functions of some variable. Like, these entries can be functions of a variable in general. But what I meant is that you saw fields, right? Like a vector field is the electric field, for example, is a function, right, of a different type of, let's say, f of x, g of x, f of x, y, and z, g of x, y, and z, and h of x, y, and z. You saw this thing? Something like this? Okay, we're not going to use it a lot in this course, so if you don't worry about it. Okay, so the idea is that the inner product for functions is written like this. So we denote it like this, f, g, okay? It's f of x, g of x, dx. This is the definition of inner product.
This is the notation that resembles it?
Yeah,
In practice.
I'm going to put, when I put 3 equals, it means the equal with 3 bars, it's definition. It's not something that you should deduce, it's something that I am telling you, this is what I'm calling an inner product. Okay?
Okay.
Okay, here we have a problem, okay? Statement of the problem. Consider fn of x defined on minus L. Here I put minus infinity to infinity, but it can be any period or anything you want. Like, it doesn't have to be like this.
When will it not be like this?
in the example we will address
Okay.
right now. So the function is defined in this interval, right? So there is no meaning on integrating overall space. Okay? Where f of nx is 1 over L x I 2 pi n over Lx. Okay, the question is, we have a function, right?
Yeah.
And we are asking, do you see this function depends on n? And this is small n, sorry. Okay, we are asking if we change the n for n, are this function, what is the inner, like, are these functions orthogonal, right? Do you understand the statement of the question?
Yeah.
Okay. When we mean orthogonal, is that nothing you have to translate it in your brains. Like nothing of this function depends on this other function. Okay. They are independent. They don't speak. Right. This is something that will help you a lot in this course. And if something is not orthogonal, then there are some dependence between them. Okay. If I have time, I will address this more carefully. Okay, so what would you do? Any ideas?
Inner product equals to 0, 0 and
Right, so let's take the inner product. Okay. Which are the integration limit? What are the integration limits?
Minus L over 2 plus L.
Right. So
doesn't it turn into the delta function of, I don't remember the name, that is 0 if n equals m and 1 if, no, the other way around, 1 if they are equal, 0 otherwise, right?
you're spoiling my class.
Sorry.
Don't worry, don't worry. Do you agree with this?
Don't we need to conjugate the
Exactly.
So negative I, right?
Right. Well, perfect. Okay, so now, do you need to have this, or can I erase it?
Can I just take a photo of this? I'm sorry for
Sure.
just write slowly.
Don't worry, don't worry.
Okay, you can take it.
Okay. So now that we are solving the problem, I will change colors. You can see the procedure. Okay. So, okay, now we have, this is 1 over L squared times the integral of minus L2 over L2, and this is sorry. Right, do you agree?
Yeah.
Right? You agree? Okay. So we know, what do we know about this function? How can we write it?
I mean, from Euler's identity?
Exactly. So how can we decompose this?
It's cosine of 2 pi over L n minus n x plus I sine.
Right, dx. Okay, so do you see clearly that this is the period of the function?
Yeah.
Yeah? So if we integrate sine over a period, what does we get?
0, because it's an odd function.
It's an even function.
Oh, even.
Sine is even, and cosine is, you say
No,
sine
sine
is
is odd.
odd.
Yeah. So
Yeah,
we cancel
right.
out.
So we have something like this, right?
Yes, I was correct, right? Yeah.
Right, yeah. And this is something, and this is the cosine. So the cosine is something like this. Let me think.
It would be to the -1 when it's 0, and then 1 when it's like, yeah. Start from there and then go down a little, I think.
Right. But it should. This is the sign.
I think it starts from -1 and then all the way up to 1 and then back again to -1.
Right. Okay, yeah, you're right. Okay, so you get the geometric idea, right? Okay. So the area under the curve would be, in both cases, 0. So if we have m different of n, this would be 0, right?
Yeah.
Do you agree? Do you agree?
Yeah.
What happens if n is 1? And if n equals m, which is the second part of the question. Okay, so we can say that these are orthogonal when this happens. But what happens when n equals m?
We have 1 over L
Right, why?
because the sine is 0, cancel out. The cosine is 1, and so we'd have the integral of a constant 1 that would be just L, and then we have 1 over L squared times L, that would be 1 over L.
Exactly. So we have, this will be 0, right?
Yeah.
0. This will be 1. We will have 1 over L. Over L. And this will be dx. This will be 1 over L squared. And this would be x Okay. So this would be L, right? Do you see it as well?
Yeah.
Okay, the thing is that I screwed up and I should have put a square root here, okay?
Oh, and then we'd have 1.
Yeah, exactly. That's the goal. This would be like this and this would be 1. And now, what do we have?
The delta function.
The Kroneker's delta function, right? So if we have this, just to be consistent, what do we have?
1 if they're equals, and then 0 odd ones.
Right. If and 0 if, which is exactly the definition. Let me erase this.
So that's true for any function that is the same but just different indexes.
For this type of functions, yeah. For this function that we wrote, for the exponent.
Specific exponent.
We're going to see that there are plenty of functions around the, like, quantum mechanics is based on this concept, okay? Which is, you can treat functions as vectors. Instead of having the dot product, you have the inner product. We will have, instead of having matrices, we will have differential operators, but it is all the same.
Okay, so we transform from functions to so-called quote-unquote vectors?
Exactly.
Okay.
Like, functions are vectors, in a sense.
Alright, so like matrices that resemble, okay, yeah.
This is the main idea, and if you understand this, like, you understand quantum mechanics. This is the machinery, the mathematical machinery behind it. This is the Kroneker's delta function, which is defined like this. Okay? Did you know that the Kroneker's delta function?
Yeah.
This is a delta. I'm sorry for my writing. Okay? Now, okay, let's talk about Fourier series.
Just so I know, when you said the sine is 0, I know because it's odd. But cosine is even because the negative parts are, if you sum them up, they are equal to the positive part?
Yeah, yes, but both of, yeah. Okay, so you say you are integrating over the period, so...
Because like that, it would be like that, right?
Exactly.
Okay.
You have the same amount of area in the left side than what you, like below the zero,
yeah.
the axis, and above the axis.
Alright.
That's the idea. We can look at it after the class,
Okay.
but I'm a bit out of time, so I will have to run a bit.
Okay.
Okay, so the idea is that we can think about functions as vector spaces. Just as we have for a vector, we have this. Right? All the functions of the form f of x. What does this mean? Do you know?
Oh, it's periodic now.
Right. This is the periodicity condition. So, as we saw, like, you can generate a vector space if you use these vectors. You create a vector space, right? We can create a vector space by using this type of functions. where n is in the positive integers. Right? Let me put this here. Okay? So, do you recall the form of the Fourier series?
Yeah. It's a superposition of all these, right? From n equals 1, maybe 0, I don't know, to infinity.
Okay, do you know the complex version of that?
Yeah, Cn times ei n over Lx.
Right.
I mean, it could be even if they're not periodic, right? Because if, say, the interval is finite, then we can create a function that would be.
Yeah, right.
Okay.
You're right. Yeah, it doesn't have to be periodic, but if it's periodic, you can. It's very easy to see.
So periodic either fine. Okay.
Right. Okay. Everything here, it's clear.
Yeah.
All of you. Okay. So now let's make a transformation. Let's see that f of n be right? Okay, this is just to put the normalization into this, into the definition of the transform, so we don't have to put it afterwards. Okay? So now this f of x, it would be okay. Now, just one sec. Do you know how do we find these coefficients?
Yeah, I think we have an integration process 1 over L maybe, or 2 or something in the integral.
Why do we have that process? Why do we integrate? What do you do?
Oh, I think I know.
Sure.
Because the Cn is like the intensity, right? Because
Okay.
it's the amplitude.
The weight.
Yeah, and then we I think if we change the space in which we talk about, instead of x, instead of k, like I think of it because we had it in waves. You think about the wave number, and
Right.
then for every wave number you want to know the weight of the function, and then
Right.
you got overall wave number, and then you get the total amplitude, something like that.
Okay, that's like a physical intuition of what these coefficients are telling us.
Okay.
But I want to know how can I get them? Like, in like, think about it in the sense of a vector. How would you get the coefficients of the vector? Like, how would you get a1 if you have the vector?
What do you mean if I have the vector?
You have this vector, right? What operation will you do to this vector in order to get a1?
That would be
just a dot x dot.
Perfect.
yeah.
you would do something like this, right?
Yeah.
Yeah, cross product.
What is this? This is making a question over this vector. Is how much of this is no A. This is not A1. How much of A is in X, right? You have to think always like that. How much of something of this thing is here? Always think it like that. So we know that now the inner product, instead of doing something like this, we know that this is this, right? How much of this function is in this? How much of this function is in this function, right? So this is integration, and that's why we have the integral, because it's the definition of the inner product, right? Okay. So the idea is that, okay. So if you want the m coefficient, let's say Cm, what do we do? We integrate over. We take the inner product of, I'm going to put here n, right? It depends on n. I'm going to take the inner product of Fn with respect to Fn.
Wait.
Sure.
No.
Question.
Sure.
So that Fn, you write the green n. Yeah, equals to the n behind the Cn. Yeah. Equals to this.
Yeah, like this n is this n.
So this n is changed, you know.
Right. Like this. You mean like this doesn't depend on it?
Yeah.
Right. X. You're right. Sorry.
Oh, okay.
I just wanted to make
What is the
emphasize this.
phi of m?
Remember we have this thing, like I think it's e to the minus, sorry I erased it. np 2 pi n over L over x, and it was, I don't know.
You wanted it to be 1 over the square root of it.
Right.
Also, we will use that notation a lot.
Yeah. This thing, this is called Dirac notation and was invented for quantum mechanics.
Okay.
We will see later on.
And we will use phi m a lot.
Yeah.
Okay.
You will see why.
So wait, I will. Okay. Thanks.
Okay. So this thing is just e to the minus I 2mp m over Lx time Cn, and this is I okay, so I need to run a bit. See. Okay. Do you agree with this?
Yeah. I just don't understand why n goes from negative infinity if we said that these would be the x's, right? The coordinates, right?
This is sorry.
Okay.
So this can run all over the natural numbers. Okay, so when we are in the real Fourier series, it's only the positive ones. When we translate to the complex plane, we allow them as well to go to the negative. You haven't do the course of Memphis Arban, I think. Okay, so in that course it will be here.
Oh, we're just starting Memphis show.
Okay, don't worry.
And what is the meaning of the right one, the Fn equals square root of Cn?
It's just to change, to have the normalization in the definition of the coefficient.
Okay,
so this, when I translate Cn here and put Fn, here I have to put Fn. I put the 1 over L, over the square root of L,
yeah.
And with this 1 over square root, it will give me this L.
Oh.
I'm just putting, since it is a constant, I can redefine it by a coefficient.
So using a different constant. Okay.
Yeah. This is something that we will be doing a lot in this course, which is normalization, which is saying that we want the things to be the delta, so this should be 1. We want things to be 1. You will understand why afterwards. Okay, so here I can put out the sum, right, from the integration. Do you agree?
Yeah.
Yeah.
Okay, so this will give me a delta. Okay, this integral, I will erase this and put it here. We saw that this will give me a delta. This Fn, I can put it outside the integral as well, right? And I will be dealing with L equals is Fn delta Mn. Do you agree? We want not Cn, we want Fn. Do you agree with this? What happened here? We saw that this integral was the delta. We have this delta. What happens with the summation when we have delta?
We get only when it's m.
Right. So we
when
have
m equals m.
And this integral is cancel the L, right? Because it's right.
Yeah, only when n equals m, and then yeah.
So we have this summation, which is which will be 1, so we have the Fn, right?
Yeah, because n equals m.
So we know how to find it.
Why did we want to do the Fn? Why did we want to do the Fn?
This is how we know the coefficients in general.
Oh, okay.
Okay.
Oh, we do the inner product.
Right. So in general, it's like this. And yeah. So now we saw the Fourier series. Now we are going to go to the Fourier transform. I wanted to show you an integral trick, but I think I will. I upload you 2 videos talking about Fourier series and Fourier transform. Please watch them. If you're physicists, it's like these are. Sorry, did I erase something?
just the no, it would be the summation of n of fn delta.
Right. This would be something like this, fn delta nm, and this would be fn. Right?
So in this is how. So what does this tell us? Like, we got that the inner product is fm. So this is the fm. So we got only one coefficient.
Right. The inner product is asking a question. Is how much of f of x is on f n?
Oh, so that's. And then if I use different n's, then I would get different n, and then I can do it
Everything.
on the entire interval.
Exactly. You can have every coefficient, and you can have all the things that compose, as you saw in waves. Every wave can be decomposed in separate perfect or single modes.
Yeah.
So this is how, like, this is the question you're asking. How much this wave is depending on this wave?
Okay, so finding the coefficients, we just do it over each m.
Right.
Okay.
Well, you can have a formula. You have a formula. Sometimes it's like you have for every single one. And if you want any in particular, that's the great thing about doing it for m, right?
Yeah.
You just have to plug the number you want
Yeah.
in the formula. Okay, Fourier transform. I have like 5 minutes, right? I have 1 minute. Are you okay if I take 2 minutes, like
Yeah.
5 minutes of your time? Do you have any problem? Okay, so the next thing is to go to the, like, did you saw Fourier transform before? Or this is completely new stuff?
What is the f tilde?
This is another function, and now, like, k is the wave number, right? So if we have, this is the inverse, like this is the Fourier transform, and this is the inverse of the Fourier transform, okay?
So if I want to find the Fourier transformation of fx, I would have to find the inverse and then.
No, so usually, like, you will encounter, like, you will have or this or this.
Okay. And I just find the other.
Right.
Okay.
So the nice thing is that these have great properties. That, for example, the derivative, if you have a differential equation, you can change it to an algebraic equation just by making Fourier transforms. We will see it in a bit. Okay, so one example is to do the Fourier transform of e to the minus alpha x squared. Can you tell me what is the name of this function?
What is the name?
This is Gaussian normal distribution. You saw it in probability.
Oh.
For sure, like.
Yeah, I know.
This is
But
the most
over
important.
sigma squared
Right.
stuff. Yeah, okay.
In general, like, this is all contained in alpha. Okay, we want to do the Fourier transform. Do you know this? You should know only one integral by heart. As a physicist, is this integral. What is it? Do you know?
Yeah. square root of 2 pi or something?
Square root of pi over alpha.
Oh,
Okay?
but I remember that the Fourier transform of a Gaussian is still a Gaussian.
Exactly. That's very important. Remember it. It will be in the very important for the exam and for understanding the concepts in quantum mechanics. Okay? So there's also an exercise. I uploaded this in my notes to the page, the web page. I will not go into the details, but it's only to plug this, like this function. You have to find the Fourier transform. You have to plug this function into here, and then you solve it and you find the Fourier transform of this equation.
Can you not erase it?
Sure. Okay, so let me just tell you some properties of the delta function and with the Fourier transform, and with that we will end the class. There's an appendix of delta function in my notes. Please read it, and if you have any question about it, please let me know. Okay, so properties. Of Fourier transform. What is linearity? If I say something is linear, what do I mean by that?
That if we have a function, for example, f equals alpha g plus beta h, and we know the transform maybe of both h and g, then we know of f.
I am going to denote the Fourier transform like this.
Okay.
Okay. If I say it's linear, what do I mean? What happens to this?
It's equals to the a of fx plus b of fy.
Right.
But x and y are functions.
Are variables. Different
How do you
variables.
do a Fourier transform of variables?
Yeah, you have yeah, these are functions. Like if f of x equal x, you can do the Fourier transform.
Oh,
That was the trick I wanted to show you. Unfortunately, I will have to upload it because, or if you want, you can come to my F G. Okay, this is linearity. You can come to my office and we can discuss that.
do we need to
Okay.
know to solve all these integrals?
Yes, but don't worry. We will practice them a lot.
Okay.
I think at the end of the course, the exam, Richard allows you to bring material to the exam, actually. But I will teach you a way to do this. If you have time, please come to my office and we will discuss how to do these integrals. Like,
Okay,
In
please
3
help me
seconds.
because I don't know.
sure. Don't worry. Like, okay, so this is f of x plus x naught. This is the shift. This is called shift. Do you know what does the Fourier transform do to this?
No.
This is a constant, okay? It's only e to the I k x naught times the Fourier transform
Oh, right.
of f of x, right?
Yeah, we did see that.
Derivative. This is what I meant when I told you that the derivative is only, it's the Fourier transform change the derivative to simple algebra. Okay. So the derivative of f of x is ik, the Fourier transform of f of x, right? And scaling. Don't worry if you don't understand this. This is your homework. So you will understand them after. Please, if you have any question, of the homework, everything, anything, I'm here to help you. As you can see, we are not a lot of students, so really, I'm here to help you get the best out of this course and to help you get the best grade possible. Okay, these are the four fundamental properties of the Fourier transform. Okay. Do you have any question about what we saw today, or of the course in general?
I just want to say that I saw, like, went a little over the homework, and do we need to know how to perform the integrals well to solve them? Because I saw, like, solving quite difficult integrals that I'm not really good at.
Okay, so yes, you're supposed, like, it's very important for this course that you get this like ability to perform these integrals fast. Don't worry if you don't know that now. The goal of this homework is to get you to that point, and during the course all the homeworks are meant to take you some time to perform these integrals carefully. If you don't know that, if you think you have to do them, like you cannot perform it in an exam by heart, like, I know what this is, please do it in the homework. If you know how to do that, you can do it in Wolfram. I don't care if you really like do each step, but if of course if you want, we can go to do some of these integrals after the class, and I'll be very happy to help you. Okay, so is any property of here like don't clear? Isn't like something clear? Of course, these are functions of k. You see that, right? Like here, the Fourier transform, it's just a function of k. Is this thing? I can substitute this here and here and here.
Okay. So here in the derivative, it would be ik of f of x.
Of the Fourier transform, yeah, right.
Okay.
Sorry.
Oh,
It will be f of x, which will be ak. Sorry, I don't have a lot. Ak, and this would be f tilde. I'm going to use this notation of the tilde to emphasize that this is the Fourier transform of a function. When I'm going to the wave number space, like when I'm talking about wave number functions, I'm going to put the tilde here just for you to have a clearer view. Okay?
okay.
Okay, so if you have any questions about the course, all the homework and the tutorials will be uploaded to the web page of the course.
So the homework on the web?
Yeah, and you can upload it there as well.
Can you check them?
Yeah.
Harshly?
Not harsh, not at all. Like, I care that you do the exercises and understand the concepts. That's what it's
So
the most important for me.
if we make computational mistakes and stuff,
I won't be harsh at all. I won't penalty for it. Anything like that. Don't worry about it.
can we come to your office and ask for help? Something?
Of course, whenever you have anything, if you want to make sure I'm there, you can write me an email.
Okay.
Or we can go after class. After today, I will have things to do after class, so I won't be able to do it.
Okay.
So
Just
yeah.
because well, the math is a little hard for me, a little difficult.
Sure, it's a bit intimidating, and
Yeah.
we cover a lot of topics. Like, as I told you, this was supposed to be a resume, like some sort of. So you can remember these concepts that you are supposed to know. But if you don't know them, don't worry. You can deal with them like carefully. Okay. So thank you very much. And as well, if you think that I am not being clear in something, if you think that like if it comes to your mind a way that I can improve these lessons, please let me know. Like I'm here for you.
Thank you.
Okay. Thank you very much.
Just so I know, because my first encounter with linear algebra was met.
Okay.
Will it be more friendly? Will it be friendlier?
I will try to do it as friendly as possible as I can. Like quantum mechanics is what we call a linear theory. So what that means is that everything in quantum mechanics follows an algorithm of linear algebra. Next class I will start the class by remembering you eigenvalues and eigenvectors very fast. Do you remember that in general? Do you recall what those are?
I don't. I mean, I've studied the first course in university as linear algebra over a year ago.
Okay.
And then I didn't touch it at all.
Okay, don't worry.
So I have to. So it's good because then it would be a new page, you know. Because I don't quite remember all.
Sure.
It would be a new page, and then I hope it would be better.
Right. Great. And you have more experience with math, so you will understand it better. I can give you a series of videos on YouTube that are amazing, explaining things about linear algebra. Like everything I know about linear algebra, yes, I went to the courses, but how to deal with that in my head and not only in the numbers that sometimes is very hard to see. And linear algebra is supposed to be very geometrical. Like it's supposed to have 10 different ways of looking at the same thing in geometrical viewpoint. So these things we are not taught in our courses. Like professors don't spend time dealing with that. That's why I will try to upload you these sort of videos.
Yes, please. I would appreciate it a lot.
What I used to do when I was a first degree student, was that when I was eating, I put those sort of videos, and I will, when I went to class, I would feel like I'm not very smart, I don't understand what's going on. Like, why for the professor is that obvious to see something, and for me, it's very hard. And what I was doing, it was like, when I saw these videos that show you the geometrical interpretation, that give you this intuition, made me feel like I was understanding all these concepts and all this math, which is sometimes dark and obscure. So I was it gave me some confidence to go through all this hard math.
I hope so. So I appreciate it a lot.
Sure. And do you want to come by now, or at any point to the office?
We'll come. Yeah.
Sure. Okay.
Thanks. Have a good day.
You too.
Bye.
Bye. Let me know if you need anything.
Okay, thanks.
Do you know where my office is, right?
Said
213?
213, yeah.
Okay. Sure.
Level 3, maybe 2.
Erase this thing. It's annoying when someone leaves it. Or do you want to go through the details now? Do you have time, or
Of what?
to the integrations and all that things? Or do you want to rest a bit?
I need to finish one of the. I mean, I can if you have time. I just need to finish some of the papers for this recitation.
Sure, don't worry. If you like, anytime you can just write me an email or come by, and if I'm there, I'll help you.
Okay, thanks.
Pleasure. And yeah, do you think everything in the lesson was clear? Like, what do you would like me to do? Like, you want me to write better? I don't know. Like,
No, it was well. It was very good.
Yeah.